So I talked about these thermoplastic waves, and I'll skip a bit technical part, which, well, I just will tell you that it's possible to develop a specific concrete model for how this flame of burning perpendicular field will propagate. It's a kind of propagating wave solution which basically converts magnetic energy to heat. One interesting feature of these thermoplastic waves and all these dynamics in the neutron star crust, which involves plastic flows and hole drift, one interesting feature is that thermoplastic waves leave behind sharp gradients of magnetic field. Because imagine if you have a wave burning the perpendicular magnetic field. Behind the wave, this field is almost absent. It's very weak. Ahead of the wave, there is a lot of B perp. So the thickness of the front of the wave is quite small. That means there is a jump in the B perp. And so if the wave propagates and then extinguishes at some point, it leaves like a footprint, which is basically a jump in the magnetic field. And this jump is an efficient generator of Hall waves, right? Because again, the jump means small scales, and small scales generate, the jump generates short wavelength Hall waves that can propagate quickly ahead of this jump. So there is an interesting nonlinear dynamics that we studied together with Yuri Levin and Xin-Yu Li at Columbia, a PhD student who did this calculation of this coupled dynamics of the Hall effect and thermoplastic flows in a simple one-dimensional geometry. And we saw this effect of Hall waves being generated by the thermoplastic waves, and then Hall waves in turn generate thermoplastic waves if they succeed in breaking the material ahead of the wave. So there is a kind of nonlinear coupling between the two processes that you can simulate numerically. And this is a this is a time history of the simulation. It's a space-time diagram which shows distance, basically depth in the crust in meters. So you see it's a layer of 25 meters. And the vertical axis is time. So it's space-time diagram. Blue means strong magnetic field, this perpendicular component that is being burned by thermoplastic waves. And white means very weak field. As you can see, color coding, white is 0 essentially. So on the left, you see the field that has been burned by the wave, by these plastic flows. On the right is the region ahead of the wave. So the wave propagates with velocity, with speed, which is basically given by the slope in this diagram, as usual in space-time diagrams. And what you can see in this diagram is these little features. So this front of the wave is not propagating smoothly. You can see repeating events of failures, kind of avalanche of failures that develop. And this avalanche is mediated by the Hall waves. You can see the Hall waves as the little wiggles you see ahead of the, in the blue zone on the right side of this main front. You see the Hall waves propagating ahead of the burning regions. These are the Hall waves that are generated by the jumps of the magnetic field left by the thermoplastic waves. And so they help this crust to break again, and then a kind of avalanche is developing. This speed of this avalanche is related to the speed of thermoplastic waves by this formula. So remember I told you that the thermoplastic waves propagate because of heat diffusion. So heat is generated in the front of the wave, and heat diffuses ahead of the front, breaks the crust there, and then the front propagates. So its speed is controlled by the thermal conductivity, which is chi here. Okay, it's more exactly it's heat diffusion coefficient. Its value in the crust typically 10 to 100 centimeters squared per second. Diffusion coefficient. So the avalanche is propagating slower, and its speed is controlled instead of diffusion of heat. It's like Hall diffusion, if you like. It's controlled by this Hall coefficient, which I wrote here, and it's now erased, dH, and which is written again here with numerical value. The characteristic value is 0.05. So the ratio of the two to the 1/2 power is basically the ratio of the speeds of the of a thermoplastic wave versus the avalanche speed, which is made of many thermoplastic waves coupled through the Hall waves propagation. Yeah?
Probably you mentioned it, but I maybe was lost. But when you say the thermoplastic waves, they propagate because of the heat diffusion, right?
Yeah.
But that is why they propagate. I mean, it's not just a damping process or a diffusive process.
It's not much different from propagation of a flame, right? So imagine you have fuel, and you light up with a match this fuel. You launch a deflagration front. So what's happening there? Fuel is being burned, right? And what it leaves behind is heat. And this heat diffuses ahead of the front. You light up the next layer of the fuel, and the front moves to the next position. So it is the diffusion of heat that allows the front to propagate. Okay. So here it's the same thing. The only difference is that instead of chemical fuel, you have the perpendicular magnetic field. Its energy is being burned, essentially. Good, okay. All right, so we can see these avalanches also. From these simulations, we can construct similar space-time diagrams. And you can see the whole wave mediated by, whole wave mediated failures in the crust. So many failures, like avalanche type failures, which propagate slower, which means steeper slope in the space-time diagram. So you mostly go along the time rather than the position. So it's a slow propagation. And well, actually, you see the two waves. You trigger it at some point, and they propagate deeper into the crust and toward the surface. And at some point, in this particular example, you see triggering a major thermoplastic wave. It propagates much faster, and it burns a lot of magnetic field quickly with a very flat slope, right? So it means high velocity. And on the right panel, you see the temperature. So color coding here is the temperature. You can see that this whole wave mediated avalanche gives you relatively hot crust with 3, 5 times 10 to the 8th Kelvin. When you came to this thermoplastic wave, this flat part, the temperature goes even high. It goes above 10 to the 9th Kelvin. So you can heat up the crust to really high temperatures for this process. All right, and of course it's a transient phenomenon. Then the crust cools through heat conduction. Most of this heat flows to the core, and then it lost there to neutrino emission. And part of it goes to the surface and makes the surface glow. Not necessarily the entire surface. It can be localized patch in the crust. And so you create a hot spot on the surface. And this simulation that Xinyu Li did, it ran for a long time, like 10 kiloyears here. And you can see spikes. Neglect the red lines here. The blue lines show the heat that gets to the surface from these events. And you can see that, wow, you can see that it failed now. No, it's okay. Oh, because I am not connected to, all right, so it's good. You can see that over the history of this magnetar, there are spikes, like transient events, when hot spots appear here and then there with significant flux. This is characteristic behavior that is predicted with this model. So it gives a nice actual explanation to the transient magnetars that I discussed, remember yesterday. There are magnetars that we'll look at and then keep shining persistently with hard spectrum for a long time, continually actually, throughout the entire history of observations, like 30, 40 years. And there are some magnetars that we didn't know about, that suddenly they switched on with the burst, like Swift satellite is looking, patrolling the sky, boom, the burst came from some direction. You look there with Chandra or New Star telescope pointing, and then you discover there is a persistent, well, now active, not persistent, but now significant source of radiation. You can analyze the spectrum of this radiation. Of course, it's luminosity and everything, if you approximately know the distance. And there are almost half of magnetars discovered through this sudden switching on. So these are kind of transient magnetars that might be described by this process in this model. All right, I'd like to also talk about different aspects of physics of magnetars, so you get a complete picture. So I'm spending like 4 lectures on that. So you would appreciate the diversity of physics phenomena that you have to think about as part of this fascinating phenomena, these ultra-strongly magnetized neutron stars. So one question you might ask, okay, I mentioned black body emission. Do you really expect black body emission from these stars? You could imagine that if you measure the spectrum carefully, maybe the deviation from black body would be a way to measure the magnetic field on the surface. Maybe if the spectrum that emerges from the surface actually somehow depends on the magnetic field. You can also imagine getting some information about chemical composition of the surface if you do careful spectral analysis. So relaxing the assumption of black body emission potentially can be interesting and can carry interesting information. Then another aspect is polarization. We don't have good measurements of X-ray polarized signal from neutron stars, but future missions, in a few years, we may have these detections. And then it would be nice to compare what you expect from magnetar and how it depends on the magnetic field, for example. So there is a subfield in this field, which is focused on how this, on the process of radiation transport in the surface layers of the star with the spectrum forms, trying to understand the shape of the spectrum, polarization, etc., lines, if there are any lines. So for now, there is just I'm not going to spend too much time on this now because there are no exciting results yet, but just to give you some idea what is involved in this problem. So here is the list. Things depend, the spectrum that you will get from the surface, just from heat diffusion from the interior, would depend on the chemical composition, equation of state, in particular whether you deal with a condensed material, condensed atmosphere, so it's liquid, or it's more like gas atmosphere, and the magnetic field, ionization degree, which you try to calculate all self-consistently. There are lots of papers on that topic. Not only for magnetars, actually most of these papers are just on thermal spectra from neutron stars. So we see isolated neutron stars nearby. I showed in the beginning, I think, some data analyzing just quasi-black body emission from nearby relatively dim neutron stars that just passively cooling with the age. And so when you begin to think about this problem, the first question you might want to ask is, what are the eigenmodes of photons? What are the modes that are propagating in this, let's say, atmospheric layer of the star? And as you know, in vacuum, you have linear polarized electromagnetic waves, or circularly polarized. You have two modes, right? Two states. When you deal with the same problem in matter, and especially in magnetized, strongly magnetized matter, you find that, again, there are two eigenstates with slightly different propagation speeds, which are linear states with linear polarization. They are called E and O mode, or sometimes X and O mode. So this plot shows the difference, how these two modes are defined. you see the magnetic field here. The z-axis is chosen along the magnetic field. Then there is the k vector. This is the wave vector of the photon. And again, so you have k and b, two vectors that define a plane. That's the preferred plane of the problem, right? Now, the electric field of the wave, of the photon, if you like, if you think of the photon as a classical electromagnetic wave for a second. So there is electric field oscillating in the wave. And this electric field could be either perpendicular to the KB plane, or it could lie in this plane. So these are the two polarization states. If the electric field is in the wave of the photon is perpendicular to the KB plane, that's the X mode, okay, or E mode, what they call. If the electric field is inside this plane, so of course it's still perpendicular to K, right? But it's at some angle with respect to B, but it's in the KB plane. That you call it O mode. Now, I think I mentioned already yesterday that even without matter, if you have photons propagating in strongly magnetized vacuum filled with magnetic field, these two modes propagate with slightly different speeds. These are the two eigenstates. Very slightly, but still enough to distinguish the two modes. And if in addition to the magnetic field you also have dense material, then the wave, of course, the photons begin to feel the presence of the charged particles. So there is some plasma response. So if you write the dispersion relation, there will be an additional term formally if you think about it. Now there is a characteristic density above which, matter density, above which the dispersive properties of the medium is determined by the plasma response rather than the vacuum polarization effect. And this characteristic density is comparable to 1 gram per centimeter cube. So in the deep interior of the star, well, not very deep, where density is above 1, let's say, or 10 gram per centimeter cube, you have wave photon properties, eigenstates, determined by the plasma response. Still two linear polarized modes. Okay, once the photon enters the region of lower density, now it doesn't care about the plasma. Its eigenstates are controlled by the vacuum polarization. The photon fills the vacuum electron-positron pairs, the virtual pairs. Now, why the distinction between the two modes is important? Because they have completely different cross-sections of scattering, vastly different cross-sections in the strong magnetic field. And it's easy to understand why. So what is written here at the bottom is the cross-section for the X mode. You can see it is much smaller than Thomson cross-section. That would be scattering cross-section in vacuum for a photon. And the suppression factor is the ratio of the frequency of the photon to omega b. Omega b is the gyro frequency in this magnetic field, which is enormous because we're talking about very strong magnetic fields. So the suppression factor is huge, depending, of course, on omega. Normally, we talk about keV photons. So like h bar omega would be 1 keV. H bar omega b, the gyro frequency translated to energy, would be basically Landau energy. Remember how the critical field was defined? H bar omega b. This Landau energy is equal to electron rest mass, 511 keV. We're talking about fields which are even stronger than electron in that sense, above this QED field. So omega b times h bar could be several MeV, for example, in this case. It's way above the keV energy of the photon. So it's a huge suppression factor. Omega is much smaller than omega b. But this is, okay, so this is the cross-section for the X mode. For the other mode, it's comparable to Thomson cross-section. So there's a huge difference. Now, the reason why there is such a huge difference is very simple. In very strong magnetic fields, particles move like beads on a wire, right? Also, I described it last time, yesterday. If you have a wave which tries to interact with a particle sitting on a rail, normal Thomson scattering works like this. The wave begins to shake the particle. The particle produces dipole radiation because it's accelerated by the wave, and it produces emission. The ratio of outgoing emission to the coming flux of the wave defines the cross-section. This is how you derive, it's a classical derivation of Thomson cross-section. So in this process, you want, when you calculate the cross-section for scattering, you want to understand how the particle moves with respect to the wave. Now, if the particle is confined to move along the rail, this magnetic field line, then obviously the wave that has electric field component non-zero along the rail is capable of shaking the particle significantly. And the wave that has electric field perpendicular to the rail is not going to shake the particle because the particle is confined to the rail. So that's simply why. So the O mode has electric field component that can shake the particles along the field line and therefore big cross-section, Thomson cross-section basically. The X mode has electric field perpendicular to omega B plane, in particular perpendicular to B. And so it does not quite shake. Well, it shakes it a little bit, but there is this suppression by the square factor. Now, the implication of this distinction, well, let me ask you then. Can you tell me, when you look at the surface of a neutron star, strongly magnetized neutron star, and there are photons streaming from the star, you would expect that one of these two polarizations would completely dominate the observed flux. Which one and why? Can you tell me? Yeah, so the O mode is stronger coupled. So the cross-section for the O mode is comparable to Thomson cross-section. For the X mode, the cross-section is much smaller. Photons in the X mode do not interact with material as strongly as the O mode. Of course, deep enough, you have complete black-body equilibrium. You have both modes like normal. But I'm saying that at the emission that actually you observe from the star will be dominated by one mode. Which one? The X mode. You can see that, right? Because the photon free path is much longer for the X mode. So essentially, if you have a polarimeter, if you have eyes which are sensitive to only one mode, let's say X mode, you see deep into the star where it is hotter and the flux is brighter. If you switch glasses and you now see only the O mode, you see a shallow layer which has less flux. So another way to look at this, well, the star is trying to emit radiation. Of course, those photons that are easier to find it easier to escape, they will mostly carry the energy flux. So your immediate conclusion would be that, well, that has to be X mode. And if you look at the star extra polarimeter, you may try to actually use that information to infer the geometry of magnetic field. As the star rotates, it becomes particularly nice because you can see it from different angles. If you resolve in the phase rotation, you get a tool of extracting important information. And you would be wrong, okay? Because there is another effect. So this effect is related to the fact that photons that propagate through the magnetosphere can still change their polarization. Because as they propagate in the magnetosphere, they track the local eigenstate. So if you emit it in the X mode, that means that electric field is perpendicular to K and B plane. As the photon propagates through the magnetosphere along the straight line, this is high-frequency photon. This is a KV X-ray. It oscillates so frequently so that it adiabatically tracks and stays in the local eigenstate. It's like in quantum mechanics, if you remember. It stays in the same eigenstate. And the magnetic field is gradually, adiabatically changing direction, the local magnetic field. And so the polarization, the direction of the electric field is going to track that change until the photon reaches large distances from the star where it decouples, where the field is basically weak enough. Now, the coupling parameter is related to difference in refraction indices. So, of course, the very fact that you have two different modes is related to the difference in refraction indices for the two states. K is the wave vector. Basically, as it corresponds to phase speed equal to the photon propagates with the speed of light. And as long as K times the characteristic scale of magnetic field change, which is radius of the star, roughly speaking, times the small difference between O and X mode and refraction index, which is written here, This is the result of QED, nonlinear QED calculation. This is the vacuum polarization effect which I talked about. And it turns out that you can explicitly calculate and get this nice simple formula. Theta is the angle between the photon direction and local B. So the two refraction indices are different. That means that the phase speed of the two waves are slightly different. And this difference times k will be much larger than 1 is the condition for this adiabatic tracking. When you go to get to the small b region, this condition is violated, and the photon just leaves with frozen polarization. And the observed polarization of that photon will be set by the surface where you have this decoupling. It will not carry the information about the polarization at the surface, or rather the magnetic field direction at the surface. Its polarization will reflect the magnetic field direction at this decoupling radius, which is 100 times bigger than the star, okay, where the field is roughly dipole. Okay. All right. So another thing that can happen with the photon in the magnetosphere is scattering. The magnetosphere, as we'll talk about it in a minute, is actually filled with plasma. It's not quite vacuum. It's low-density plasma, but there is a significant probability for scattering. Now, I just told you that the O mode and X mode have these cross-sections. It turns out that these spontaneous cross-sections are not really so big so that they can affect significantly the transfer of photons. But there is another process, resonance scattering, which does affect and has significant probability to happen on the way out between the surface of the star and infinity. So there is some plasma particle, let's say electron, in the magnetosphere, which can scatter the photon, KV photon propagating from the stellar surface. And this scattering, resonance scattering, is a rather simple thing. It's just, you can think of the target, the electron, living in the ground Landau state. Then a photon comes, and if the energy of the photon matches the difference between first Landau level and the ground state, this h bar omega b, then the photon is absorbed and immediately emitted. It's one way of thinking about this resonance scattering. It's absorbed and re-emitted in a different direction. Okay, this resonance scattering process. The cross-section for this resonance scattering process is much larger than the Thomson cross-section. Okay, it's actually given by, remember, Thomson cross-section is roughly classical electron radius squared times 8 pi over 3. That's the Thomson cross-section, 10 to the minus 24 centimeters squared. Right? So that's classical electron radius, something like 10 to the minus 13 centimeters, right? The characteristic scale that you can make from electric charge, electron mass, and speed of light. Now, Thomson cross-section is basically this classical electron radius squared. Now, this resonance scattering cross-section is of the order of classical electron radius times the wavelength of the photon, rather than, so the ratio between the two is the ratio of lambda to Re. And so this thing is 10 to the minus 13, and this is much bigger. It depends on the, well, if it's KV photons, one angstrom, basically, it's much bigger. Right. So, of course, to achieve this resonance scattering, you need to match the photon energy to the local magnetic field strength. So you need the condition omega is equal to omega b, which is the gyro frequency, magnetic field times electric charge divided by electron mass and divided by c. Right? That's the resonance condition. Well, strictly speaking, this condition needs to be satisfied in the rest frame of the electron. Okay, so when you have a photon and the electron is moving, and typical electrons are moving with high Lorentz factors, you first calculate the Doppler shift of this photon to the local rest frame of the electron, and then you check whether you have resonance condition. And in general, you wouldn't have this condition satisfied, but as the photon propagates, it probes all magnetic fields, right? It goes to low and low, and it finds the resonant surface. It finds a location where it can be scattered with this resonant cross-section. And So the probability for this process is very high. So even though the density in the magnetosphere is not so high, the scattering actually affects greatly the spectrum. So most of the photons actually get, many of them are scattered. So that has an interesting effect, of course, immediately if you think about it. Okay, if many of the photons flowing from the stellar surface are scattered, I don't quite see the surface directly. What I see is scattered radiation. And therefore, the pulse profiles that I showed in the beginning are not coming from hot spot rotating on the star. There may be a hot spot. It's rotating, right? Okay, it would produce some pulse profile. But what I see is actually reprocessed somewhat. So like half of the photons, let's say, scattered due to this resonance scattering. They change their direction. Obviously, they don't smear out completely the pulse profile. We'll still see strong modulation of the pulse profile, but it's changed. So the pulse profile knows about plasma existing in the magnetosphere, which complicates the problem a little bit. Another thing that happens in scattering is that you tend to switch the polarization state. When you emit, so again, resonance scattering, you go from the ground state to the first state. The difference between the two states is this h bar omega b. Again, b QED, this characteristic field, is such that h bar times E is equal to MEC squared. That's how it is defined. This is 4 times 10 to the 13 Gauss field, and we have fields stronger than that. So this energy is like, it's more than 1 MeV. Near the star. But as you go away from the star, the magnetic field drops. Like if it's dipole field, it goes as 1 over r cubed. And then the photon finds, the KV photon finds the place where h bar omega b is close to KV, and it will be scattered. And so in this scattering event, the photon that is emitted, so you absorb the photon and emit it back with different direction and with different polarization. It can be emitted in a new mode. And it turns out that it's 75% you switch from, 25% probability you switch from X mode to O mode. Again, it's very simple and exact result, which tells you the effect of scattering on the polarization. And so when you measure the polarization, it would enter what you see. All right, now let me move to what happens in the magnetosphere and why there is any plasma. Okay, so remember, magnetars are very slow rotators, and really the rotation is not a significant source of the plasma. Not much matter would be lifted because of rotation. There is another effect which makes sure that the magnetosphere of magnetars has plenty of plasma. It is also related, like in pulses, it is related to electron-positron discharge, but it's driven somewhat differently. It occurs in closed field lines, not open field lines. Remember, in pulses, we had two kinds of field lines. Those that were open went to the light cylinder, and there was electric discharge happening mostly in the separatrix and the Y-shaped current sheet between the open and closed zone. And so here, the open zone is nothing, because if you have 8-second period rotation, omega is like 1, this 1 radian per second. That's the rotation angular velocity. And so if you calculate the light cylinder is c over omega. That's the distance where you have distance from the rotation axis. That's the velocity of rotation. If you equate it to c, you find the light cylinder, which is c over omega. And if your omega is 1, this is the typical omega of magnetars, and this is 3 times 10 to the 10th, you find huge light cylinder radius, 3 times 10 to the 4 times bigger than the radius of the star. So it's so far that the tiny amount of, well, that's the star, and that's the light cylinder. And so, okay, I'll exaggerate, that's the star. Most of the field lines will be closed, and only a tiny fraction of the magnetic flux that goes all along this eventually will cross the light cylinder. So there is almost negligible open magnetic flux. All the activity that we see from magnetars comes from the closed zone, which would be completely dead in the case of pulsars. Okay? So now, of course, one would like to understand why closed zone of magnetars is active. And the reason is simply because of the effect that I discussed earlier today. You have surface motions that twist up the magnetic field lines, and by shearing the magnetic field lines, they create curl B in the magnetosphere. Once you create curl B, there must be electric current that sustains curl B. Now, okay, so, right, there would be electric current, but you need particles to carry this electric current. So what happens if there are no particles? Because remember the hydrostatic scale height of the atmosphere, because of the huge gravity on the Newton star surface, it's tiny, it's a few centimeters, and then density is exponentially reduced. So you would think it's basically it should be complete vacuum. How do you get particles? There is electron-positron discharge that generates particles. So basically, once you begin to twist up magnetic field lines, you generate, through induction effect, you generate electric field that accelerates particles, and then they produce high-energy photons that convert to pairs. And that's how the magnetosphere is populated with pairs. Now, this is, of course, a dissipative process that it ultimately feeds the persistent X-ray emission that we observe from the magnetosphere of magnetars. And if you just look at it simply, zeroed approximation, if you compare magnetars and pulsars, the central formula will be written here in the center. Power that you see, luminosity, is fed electrodynamically. It's the product of the electric current flowing in the system with the voltage which sustains that current. That's it. It's like a resistor in an electric circuit. That's all that is happening. This lightning that produces continual lightning that keeps the discharge going in the magnetosphere is associated with certain voltage. Curl B that is imposed by surface motions onto the magnetosphere is associated with certain current. And the product of the two gives you the power that is radiated eventually from this system with a non-thermal spectrum, because it's all happening in the optically thin, not very opaque region, the magnetosphere. Okay. All right. I won't go into much detail, but you already have all the ingredients to understand actually this phenomenon. So what happens here in this diagram on the right at the bottom, above it is a nice picture of a solar flare. It's actually a real picture in H-alpha, snapshot of an active flare region on the sun. So what happens in magnetars is that, unlike solar corona, you don't have much plasma initially. So you have this surface layer dense, which produces which produces a lot of keV photons actually flowing through the magnetosphere. Now, once you have a seed particle moving along the magnetic field line that has been twisted and therefore would like to conduct current, and it's missing this current, okay, it's missing the current, which means that you are trying to create curl B by motion, and curl B is equal to 4 pi over c. That's the conduction current, but there is an additional term in this equation, displacement current. And so if you are missing this current, it means that you will generate displacement current. That's the electric field that is going to accelerate whatever particles are there, some seed particles for the avalanche of pair creation, that will make sure that actually in the end you will have enough conduction, enough plasma to conduct the current and support curl B. So if you place initially a seed particle, let it be accelerated by this induced electric field, then even in the strong B region, where it's hard to satisfy this condition just because B is so strong and omega B is much higher than omega of your photon, you can still reach the resonance if you accelerate your electron, your target for scattering, to high Lorentz factor, let's say 1,000. Because then, in the rest frame of that electron, the keV photon will be blue shifted, right, by Doppler effect, by a factor of 1,000. instead of keV, it will become 1 MeV, and it will match the resonance, and it will do the resonance scattering. So essentially, the mechanism of driving the discharge near the star is very simple. There is electric field, it accelerates a particle until it reaches the Lorentz factor, roughly 1,000, at which it begins to resonantly scatter background keV photons. And once it begins to scatter these resonant keV photons, it will boost them by gamma squared, because the scattering, it's a scattering of energetic particle. The photon will gain energy. It's a pure kinematic effect. So if you have a moving target, the photon comes on the lab frame, it's a keV photon. If you look at this in the rest frame of the moving electron, it's a GeV photon, let's say. Then it was scattered, it changed its angle, and it's still a GeV after resonance scattering. It has the same energy in that rest frame of the electron. But when you transform this back to the lab frame, because of the changed angle, on average you get another factor of gamma. So gamma times gamma is the amplification factor of gamma squared. Same as inverse Compton scattering. So inverse Compton scattering does precisely that. Moving electron with high velocity upscatters photon and energy by gamma squared. Same kinematic effect. And so this accelerated electron begins to produce high energy resonantly scattered photons, moving the photons above GeV energy. And these upscattered photons, of course, don't survive in the strong magnetic field. They immediately convert to pairs, and that's how you launch the avalanche of pair creation. Now, this kind of picture can be simulated directly using the PIC method that was discussed last week, and I talked about yesterday in the context of pulses. So one can do could set up a similar numerical experiment where you have a star, an atmosphere around the star, very thin one. That's the source of seed particles that can be lifted by electric fields. And then you add some simple version of that physics where induced electric fields would generate high energy particles, and these particles will produce resonantly scattered photons. So what happens then is that you begin to fill the magnetosphere with plasma. So let me show this. Well, this movie will show electric current again, J divided by B, normalized by the local B. But it will be just red color. You can see how the magnetosphere, what's happening here is that you start to turn one part of the star with respect to the other. You begin to twist the field lines. So initially, there was no twist, there was black, no current. Then this plastic flow, idealized picture, just axisymmetrically begin to turn one hemisphere with respect to the other. Imagining, okay, there was some deformation happening inside the crust. It begins to twist up the external magnetic fields. And you launch electric current, as you can see in this movie. It flows pretty much everywhere initially. Then you stop this twisting motion and you wait. And as you wait, you begin to notice that there is this black cavity. So, of course, the white circle is again the Newton star. And next to it, inside this bundle of field with electric current J, this J bundle, there is a growing cavity. You see how it grows more and more with time, slowly. This is an effect that actually can be explained nicely analytically, and it's related to the fact that the discharge has a threshold. So there is a sharp voltage threshold for creating the avalanche of pair creation, which translates to rather sharp boundary of this growing cavity. And the reason why cavity expands is basically it feels the presence of the very good conductor at the center. So basically it expands from the ideal conductor, this white circle from the center, and filling more and more space in the magnetosphere. So I'm not going to describe in detail this effect. You would need to believe me that this cavity is expanding with certain velocity that can be calculated analytically. I'll better move on to flares of magnetars. But the nice part is that this prediction that you can see here, it's like first principle simulation. This prediction has important observational implications. In particular, if you imagine something happened to the magnetar it launched this current. Then you let it evolve on a slow resistive time scale, which is like a month. And there is this cavity growing in the magnetosphere. What would be the observational effect? One observational effect that you would expect, you see the footprint of this J bundle is shrinking with time. So the hot spot on the star, if you're able to see that hot spot, becomes small and small in size. And so one prediction here would be that following an outburst event, you might expect, and this expectation seems, I mean, at first sight seems naive, and I mean, it would be nice to see shrinking hotspots on a star, but because it's very specific prediction, right? I mean, you have a spot which is initially bright and then shrinking. And its luminosity is decreasing with time, and its area is decreasing in time according to concrete formula, well, approximate, but still specific formula. So the nice part here is that actually the shrinking hotspots are observed. So let me show this little piece of data on the right. This is luminosity versus area for hotspots that have been detected in magnetars. And as you can see, the evolution, different colors mean different objects. And so if you look, for example, at blue plots, that's a kind of famous XT1810 famous magnetar, which is a transient object, which was also observed as a radio pulsar. That's the first magnetar that was detected as a radio pulsar. You can see how the area, so different blue circles are observations of the same object at different times, and the observation started at the upper end of this sequence, and you can see how the object evolves towards smaller and smaller areas and smaller luminosity. So the spot is shrinking and becomes dimmer. And the two lines is roughly the expectation from this theory. Still idealized, keeping the voltage fixed, but in a reasonable agreement with the data. All right. Well, this plot shows the dependence. I mean, what happens basically in pair creation, right? So this is what happens here is that you inject a particle in the upper corner of the, yeah.
Oh, sorry. What were the wave simulations?
How long? Yes, the simulation with the current. Oh, yeah. So the initial waves are Alfvén waves, essentially. So when you begin to move the surface, you launch Alfvén waves. These are shear waves. And these Alfvén waves propagate into the magnetosphere. They go to the other foot point. Some of them are reflected. And then over time, you establish a quasi-steady set of, picture of the current. These are the waves. But also you see, longer-term evolution where the shape of the J bundle is changing with time, particularly as cavity grows and everything. Now, what's happening inside the J bundle, it's continually filled with plasma, electron-positron plasma, and this is the avalanche picture. It's shown in the plane of magnetic field on the horizontal axis in Lorentz factor. So when you inject one particle, just a single particle, at magnetic fields in units of the QED field of 10, so 10 times 4 times 10 to the 13. So it's 4 times 10 to the 14 field near the surface of the star. And you give the particle, you accelerate it to a high Lorentz factor of 1000 and let it propagate away from the status to lower magnetic fields. You can just trace this particle and see what happens. This particle is moving through the bath of KeV photons, and it will scatter some of them. And each scattered photon will convert to a pair, initially at least, for fields which are not too weak. And as you can see, there are more blue crosses. That means new particles are injected. They all came from this initial primary particle. Then these blue particles also move away from the star to low and low magnetic field until they come to this kind of valley where they all congregate, and that's because they feel radiation drag. This resonant scattering steals energy from the particles. And so they follow a characteristic track their gamma is decreasing, Lorentz factor is decreasing as they go away from the star to lower fields because they lose energy to scattering. Okay, so the nice part of this avalanche that you actually there is a well-defined Lorentz factor of this outflow as a function of the magnetic field. And why I'm showing you this plot is that it has another observational implication. Once you understood what is the Lorentz factor of the most of the particles that flowing out of the star in this kind of electron-positron fountain, you can actually predict what is the emission spectrum. The emission spectrum are these photons that have been resonantly scattered but did not convert to pairs, but eventually escaped. Some of them convert to pairs, but those that were produced in weaker magnetic fields some distance away from the star, they actually escape. And so they produce no-thermal X-rays that we should observe. That would be the emission from this electron-positron fountain. This emission is produced by particles with well-defined Lorentz factor. So this flow has gamma is a function of B, well-defined. And so you can calculate everything. You can just predict what would be the spectrum of this electron-positron fountain emitted in all 4 pi direction, or if you like, you can look at it at different directions if it has a finite size, this fountain, and you can look from different angles and calculate its spectrum exactly. This panel shows the result of this calculation. The spectrum emitted at different angles with respect to the magnetic axis of the star, which is the vertical axis in this plot. So you have this little prediction, which is quite simple, again, simply because you know the Lorentz factor, and you can compare it with the data. In the end, what you want to explain is the spectra, like in the middle here in particular, or here on the right. Remember I told you and showed some data that magnetars have 2 component spectra. They have soft X-ray emission, the KV peak, and they have this hard X-ray emission, which was discovered 15 years ago and was completely unexpected discovery. So it turns out that this 100 keV peak is produced by this electron-positron outflow. At least it fits the data nicely. You see the curves that are shown here are basically the fits to the data. And moreover, for about 5 objects, this fitting procedure has been applied to the phase resolved data. So you're looking at this fountain. As the star is rotating, you're looking from different sides. You know its spectrum, this predicted theoretical spectrum, and so you expect a certain variation of the observed spectrum with the phase, with the rotational phase. And that's what you see. What you observe in magnetars is that their spectra change wildly with rotational phase. The spectrum, if you make it phase resolved, you will see different spectra from different angles. This is the observed effect, consistent with that picture. So I wanted to show that because I thought it's kind of nice. Let me tell you more about magnetic flares, and in particular giant flares. These are the most impressive phenomena, of course, that we see. I discussed yesterday the March 5th event. That's the discovery of magnetars, basically. There are 2 other giant flares with very similar light curves, similar power. December 2004 was actually even brighter, the initial peak. But the tail seems to be the same. One puzzling feature of the giant flares is that this tail that lasts 6 minutes is always the same. It lasts 6 minutes. It has about the same luminosity. The total energy radiated in this tail is 10 to the 44 ergs. It's like a machine that does the same always. Unlike many, in astrophysics, we got used to objects that do wild things, like you look at blazars. You don't know what to expect, like tomorrow, and they can do various things. If you look at an accretion disk, it can go hard state, soft state, intermediate state. It can do various stuff, right? Here you are looking at a giant flare. Or you think about solar flare. Solar flares are all different also. And here you see amazing regularity in these flares. So they do always the same thing. They have a very bright spike lasting 0.5 seconds, which can go up to 10 to the 47 in luminosity. And then there is a tail, rotationally modulated tail lasting 6 minutes. pretty amazing. And the question is why? Why there is a tail? Why there is a spike? Now let me talk a little bit about the tail first. So the only way to have a rotationally modulated bright emission is to confine the source of the plasma. The source of the plasma emitting radiation. So if you have magnetic field that is strong enough to hold the bright plasma cloud in place and make it co-rotate with the star, then the source will modulate the emission that you see. If the plasma pressure is larger than the magnetic pressure, it's not going to stay there. It will just, it will leave the system. There will be no rotational modulation. So the fact that we see this modulated tail, which have significant lifetime, means that there was plasma cloud, which is capable of emitting bright non-thermal radiation, that is trapped by the magnetic field of the star. And back in 1992, that was actually the first Paczynski argument by Bogdan Paczynski, and Thompson and Duncan also made a similar argument in the same year. They realized that simply by equating the energy budget of the tail, 10 to the 44 ergs, to the minimum magnetic field energy, pressure, if you like, times the volume, that you need to confine, right? You get values for the magnetic field comparable 10 to the 15 Gauss. So only magnetic field comparable to the 10 to the 15 Gauss would be capable of trapping that bright source of radiation. Just pressure would be strong enough. And another effect that Paczynski discussed in particular is that this luminosity of that source, 10 to the 44 ergs emitted over 4 minutes, 400 seconds, so 10 to the 42 ergs per second, is vastly super Eddington, right? So you need to confine it with magnetic field, but you also need to find a way to produce this high luminosity despite the fact that the photons are coupled to the plasma, right? So what limits luminosity normally when you have a lot of plasma is its optical depth, okay? So radiation is going to be trapped in the plasma. So what they realized that there is a simple way of letting radiation out precisely because there is one of the modes, this X mode, with suppressed cross-section of scattering. So the O mode is trapped and it cannot produce the flux that we see. But the X mode photons are so efficient in escaping this cloud that they can actually carry the observed luminosity. And then when you do the detailed calculation, you find the luminosity that you see, 10 to the 42 ergs per second, for the same magnetic field. Again, the cross-section for the X mode is sensitive to the strength of the magnetic field. And the field 10 to the 15 Gauss is the right field to give you the observed luminosity. Okay. Right. Another thing that happens in giant flares, I mentioned it briefly, here is the Fourier spectrum. It's the time series, right? You see flux, it's modulated by rotation with, let's say, a few second period, 8-second period, in the case of March 5th event. What you find in addition, which was reported like more than 10 years ago for one of the giant flares, is the quasi-periodic oscillation of much higher frequencies, at tens to hundreds to even kilohertz. And those were interpreted as shaking of the star itself. So it's like, you know, helioseismology or you use normal seismology. You can use earthquakes to probe the interior of the Earth with great success. You know that the Earth has a core because of this analysis. We know what happens inside the sun because of helioseismology. We analyze the modes, how the surface of the sun breathes. And so by reconstructing what's happening in the interior with these modes, we can know precisely what's the temperature in descent and stuff like that, what's the density profile of the star. So helioseismology is a very powerful science that can tell you, it allows you to see what happens inside opaque bodies just by studying their oscillations. So similar oscillations have been detected in the X-ray light curves after giant flares. And it's a window, basically, to see what's happening inside the neutron star. Pretty exciting. On the right, you see eigenmode, which from one particular eigenmode, which can be excited by a giant flare. So giant flare is a way to knock the star a little bit from outside, if you like. Or maybe you can, if a magnetic explosion happened outside the star. Or maybe the trigger was inside the star. Well, again, you excite the star inside, and it begins to shake a little bit. Of course, it will be oscillating in its eigenmodes. So you have to understand what are the eigenmodes of this complicated system. And there was many papers devoted to this topic, trying to analyze first eigenmodes of this solid crust. This is relatively simple, shear waves, basically, elastically supported. Then it was realized, Yuri Levnich realized at first, that you have magnetic field coupling the crust to the core, and therefore you have to think about, even when you focus on the oscillation of the crust, you have to focus on the coupled system. So you cannot think about the crust separately from the core. If they oscillate, they have to oscillate together in the global mode. Then you have to think about how to describe these eigenmodes, what their spectrum would be. So it's developed in a subfield in this field. And I think the main conclusion from there, I think the most interesting, is that by comparing the predictions from theory for the eigenmodes with the observed QPOs, you find a huge hint, basically evidence, for superfluidity inside the core. Neutrons have to be superfluid. Because superfluidity helps you to decouple this mode from this neutron background. Neutrons are not involved as much. Effectively, the inertial mass of the oscillating material is less when the neutrons are superfluid. And you need this to get the high frequencies of the oscillations that we see. Well, just another picture of the solar flare. Now, what is a flare? Flare is a magnetic explosion, and the simplest picture of the flare is, it's shown here. It's an axisymmetric picture. When you gradually drive suppose again, we look at the star and you take one hemisphere and turn it slowly. Every field line that is attached to the star will be twisted, like one footprint is moving away from the other in azimuth, right, in phi. So it creates a toroidal field. If you keep doing this, you will generate more and more toroidal field. When the toroidal field becomes comparable with the poloidal field, let's say dipole field, then one can show that the configuration becomes unstable. The reason is quite simple. The toroidal field produces magnetic pressure, and this magnetic pressure tries to push away from the star. And at some point, the system becomes globally unstable, and simulations have been done, in particular by Carl Parfrey of this process in this axisymmetric geometry. Here is the snapshots. So that's what is happening in the simulation is precisely what I described. You take part of the star and rotate it like this slowly. And you see how the magnetic field outside the star changes. The curves are the magnetic field lines. One of the curves is thick, just to highlight one of the field lines. And the color is the density of the phi component of the electric current. So what you basically see in this progression, so psi is the twist angle. That's the angle over which you have rotated one hemisphere with respect to the other. So psi is the angle that is growing as you impart more and more twist. You eventually and suddenly you come to this unstable point, which is the fourth panel, right? His lower panel on the right, or this other point. You can see the reconnection event. So it's a way to set up magnetic reconnection in a very clean form. So the reconnection is driven by the expansion, poloidal expansion of field lines. You can see how this highlighted thick black curve, one of the magnetic field lines, how it inflates away from the star. And how eventually, after reconnection, it snaps back to the star. And like in any reconnection event, we now know there are many simulations of relativistic reconnection and non-relativistic. You create many plasmoids of all scales. It's a plasmoid chain. It's a self-similar chain of plasmoids that are ejected from the system. So effectively what happens is that you impart more and more magnetic energy, and then you have a discharge in the system, magnetic explosion that ejects plasmoids, dissipates part of the energy, like 1/4 of the energy, locally into heat. And that's how you create this hot plasmoid that is trapped by the magnetic field and co-rotating with the star and emitting the tail. That's the basic picture. Of course, realistically, this would not be axisymmetric. Realistically, it's a more complicated three-dimensional configuration. But it's something like that, right? That's the most plausible picture of the giant flare. Okay, that's the movie. Who would? Oh, it's time to wake up. So there's one movie. You're waiting for that for an hour. Right. I don't know if it's exciting or scary, but it's a movie. That's all I got. Okay. It has many lines, many curves, and they have different colors. So, okay, I'll tell you something about the color. The color basically is the ratio of B phi to B. It tells you the angle, how tight this spiral is. Okay, so the movie will shows 4 slices of poloidal field lines like this, and then another, like 4 quarters. Of course, axisymmetric. Every slice does the same as the other slice. It was Kyle Parfit, who did this movie, thought it's nice to have 4. So let's start. You see turning of the hemisphere begins to twist up the magnetic field lines more and more. You can see how there is more blue current, and you see how the field becomes more and more twisted. Yeah. It is scary rather than exciting, yeah? Yeah, I was not sure how to classify this movie. So there's more and more B phi. You can see the field is becoming more and more in the phi direction. And especially, there was the first snapping event, but it's not the end. They will begin. You keep twisting. There was another one. So here there will be more. So if you keep twisting, you basically build up B phi, and then it reaches the instability threshold, it relaxes back. Again, the field lines become red in the interesting region, while there is blue on the outside, because actually here we also included rotation and brought the light cylinder sufficiently close to the star. So there is a lot of blue outside. But if you focus on the region that is after relaxing now, is all red, right? It's not twisted. It's the closed magnetosphere. Now you can see how it's turning more and more blue because it's twisted by the continuing motion of the surface. And how, okay, the next cycle we didn't see, but then it ejects plasmoids and relaxes. All right, and I have maybe no time now. Yeah, I have a couple of minutes. Let me tell one more thing, one more interesting piece of physics that is related to these giant flares. Right, so I'm not talking about radiation physics, how you produce emission, but I hope by now you can understand basically what's happening is that you dissipate energy, create a lot of electron poised from plasma. These are huge energy densities. It's completely thermalized fireball trapped in the magnetosphere, and then it evaporates with time. And you can calculate theoretically its lifetime, and it's going to be 6 minutes. Okay, that was the nicest part, I think, of the magnetar theory. Thanks to Thompson and Duncan paper in 1996, they did this calculation. Basically, layer by layer, as you cool down this fireball, it emits photons, mostly X mode, of course, from the surface, and it begins to lose its pairs because the pair population is only supported by continual collisions between photons. 2 photons convert into electron-positron pair, then the pairs can annihilate back. So as the fireball cools, it shrinks because it begins to lose layer by layer its pair plasma. And eventually it evaporates completely. And this process takes 6 minutes. So this is the radiative aspect of this problem. There is another aspect, which is the excitation, as you saw in this movie, excitation of Alfvén waves. The thing was like trembling a little bit. And then you can ask what happens with these waves, right? So once you have an explosion, an excitation of the magnetosphere, same happens in solar flares. You excite the magnetosphere of the sun, the corona, but here more dramatically. These waves begin to propagate. Alfvén waves have to propagate, as I hope you know. They have group speed along the magnetic field lines, so they're trapped. Alfvén waves are shear modes, So magnetic field this way, if you excite the magnetized medium in the perpendicular direction, let's say, the shear wave will begin to propagate. It propagates because magnetic field lines have tension. It's like it's this normal wave supported by strings. It's the same thing, shear wave. And so once you excited these waves in the magnetic field lines, they propagate along the magnetic field lines, but these field lines are closed. So they are trapped in the magnetosphere. And what they can do, they can reflect from these walls at the heavy material at the foot points, and they would keep bouncing. So the idea that was proposed by Thompson Duncan in that paper, 1996, is that the fireball hitting the dissipation mechanism that produces that heat responsible for this pair creation and emission is related to dissipation of these alpha waves. So they develop a cascade, turbulent cascade. The wave scale becomes shorter and shorter. They come ultimately to so short wavelengths that they comes to the dissipative scale, what they call. Any turbulent cascades cuts off at the dissipative scale, and the energy flowing to a smaller scale eventually dissipates, given to the plasma. It turns out that in addition to that, there is in fact an even more important and interesting process, which I'll briefly describe now, and then we'll stop. So this process is the following. When the alpha wave propagates toward the surface, yes, there is very dense star, and when it comes to this wall, to zero approximation, you would say it's like a string attached to a wall. If I excite the wave, it comes to the wall, it's pinned here, right? So it will reflect back. That's what any wave would do. Now imagine that the wall is not quite rigid. Of course, in reality, the crust has a density gradient. So when the wave comes into denser and denser material, it goes through a certain gradient scale, typically 100 meters for the crust. And it turns out that it gives the opportunity for the wave to tunnel through into the crustal material. And one can calculate exactly what would be the penetration coefficient as opposed to reflection, transmission versus reflection. So, and this simple calculation that one can do, if you know, I mean, basically it's one-dimensional wave equation with the constant tension is provided by magnetic field line, but with variable mass, right? So the wave speed on the string is determined by the inertia of the string, its mass density, and its tension, right? So here tension comes from magnetic field, let's say 10 to the 15th field is fixed every way going to the crust, but the mass load is increasing as you go into the crust. And so the wave speed is changing as you go to deeper and deeper layers, density goes up. That means the wave becomes slower and slower. Now, if the wave becomes slower and slower, but it still has to carry the same energy flux, it means that also, of course, it has the same frequency. The slower wave with the same frequency has higher wave number. So the wave shrinks, the wavelength shrinks. As the wave comes from here with 1 kilometer, let's say, in wavelength, comparable to the magnetosphere, comes to the crust and begins to enter that medium, the wavelength begins to shrink in proportion to the inversely proportional to the density, essentially, a square root of density. And as it shrinks to the scale, which begins to be comparable to this gradient scale, the thickness of the hydrostatic thickness of the crust, 100 meters basically. If it scales from 1 kilometer to 100 to 10 meters, this wave will not be reflected anymore. It will penetrate into this material. The penetration happens only if the wavelength is larger than the gradient scale. If it treats it as a discontinuity, then you have a reflection. If the wavelength is smaller, it's like it will just enter through and propagate through the medium. So one can solve this one-dimensional problem for the wave propagating along the variable string of a variable mass and find that the transmission coefficient is 0.1%. 90% of the wave is reflected and 10% is transmitted. And as the wave, that means that after 10 bouncings, the wave energy goes into the crust. What happens next? This wave is compressed, its amplitude is reduced, but its strain, it turns out, again, it's a simple calculation which I don't have time anyway to show, but it's a very simple back on the envelope calculation that shows that the strain in this wave, that is the derivative of displacement, is actually growing. And so as the wave enters the crustal material, it begins to break it. So it becomes very short. The strain becomes very large, more than 0.1. So it begins like small and oscillating faster on a smaller spatial scale. And it begins to break the crust. It drives this, it inevitably drives these plastic flows, which is the dissipative process absorbing the wave energy. Now what it does essentially, it deposits its energy at the bottom of the liquid ocean of the star. It comes, of course, from the ocean. There is no rigid material. It just comes all the way to the bottom of the ocean. Ocean is about 100 meters in depth. Then this rigid crust begins. Then it breaks this crust, deposits its energy, and melts the crust. And you can calculate how the ocean depth is increasing in response to this heating by simply equating the energy that comes from the wave with the heat capacity that you need to melt this material, the energy that you need to melt the material. And you can estimate how deep will be the layer that you melt in this way. And this is where the wave energy is absorbed. So it's a simple and nice calculation which has a definite answer, which tells you at which depth the energy of this wave is deposited. And then it will have a very simple and nice observational effect. You see it outside, there was a giant flare. You saw this horrible giant flare, it's gone. Now, part of the energy of the flare went into Alfvén waves. They are also now gone quickly, 10 bouncing in a few milliseconds, gone into the star. Then you sit to wait for a month. The energy of these waves has been deposited at hundreds of meters below the surface. What happens with that energy? Most of it will go conducted to the core and lost to neutrinos. About 10% will come back. It will come back to the surface and create an afterglow of this event. And so if you wait in a month, and that's what the calculations that were done, you actually expect glowing of the surface with a delay. And this afterglow of giant flares is actually observed. There are a few theories. I described just one, but this kind of clean way of creating an afterglow in the physical world. I have to stop now, right? Because it's. Do you have any questions?
So, as these Alfvén waves propagate along the magnetic field lines, does it depend on like the size of the system? Because you need like, let's say, 10 oscillations. Or what if the surface is cooling, like the crust or whatever?
Yeah, the surface is cooling. Yeah. So what?
Cool quicker than the waves propagate.
Oh no. Right. I understand the question. So the characteristic time scale for the wave propagation in the magnetosphere is 1 millisecond. These waves propagate in this force-free regime when the inertia is dominated by the magnetic field itself. Plasma weight is nothing, zero basically. Plasma only produces electric currents. So these Alfvén waves move with the speed of light in the magnetosphere. When they enter the crust, or the ocean first and then the crust, they of course are much slower by a factor of 100, let's say. The typical velocity would be 10 to the 8 centimeters per second, but still they cross this 1 kilometer thick crust very quickly, in less than 1 second. While the heat diffusion time is a month. So it all happens like this in a second. The heat has been deposited, the waves are gone, and then you just wait for a month and the heat gradually diffuses back. Only part of it. Most of it, of course, will diffuse toward the core simply because, it has large heat capacity, and if it sits there, if you heat from outside, it will tend to absorb that heat. Yeah. Yeah?
Maybe I think I lost the point in certain moment when you were talking about the photon cascade. And one of the main key ingredients is that the electrons see like the blue shifted incoming photons.
Yeah.
But to do so means that the electron is relativistic.
Yes.
And why this?
Why relativistic?
Mm.
Yeah, that's the Doppler effect, right? If you have a photon and you have an electron moving with some Lorentz factor gamma, right? The photon has energy E, h bar omega. And so when you ask the question, what's the energy of the same photon in the rest frame of the electron, you do the Lorentz transformation of the form momentum of the, right? So you need this high Lorentz factor to achieve, sorry?
How can you, the question was, how do you obtain a high
What's the physical mechanism to give it high Lorentz? That's the electric field. The electric field accelerates particles. So when so if the crust is moving even slowly, it induces significant electric field. It can pull out particles, can accelerate them. And if you are missing particles to conduct the current, that magnetic field, of course, is the boss in this problem, because magnetic field is so dominant in the uppermost layers in the crust, in the magnetosphere. B squared over 8 pi is larger than anything there, than rho c square, like rest mass density. And so magnetic field, because it was attached to this deep heavy interior, has the wish to become twisted. It finds a way to generate plasma to conduct the curl Bj current, and it finds it this way through inducing the electric field that will pull out particles. The seed particles will begin to scatter photons because they are Doppler shifted to the Landau resonance, and then these photons begin to convert to pairs. You have the avalanche.
Yeah, just a curiosity, because I guess that for what concerns the outermost regions, maybe also like the intermediate regions of the neutrons, like the crust and the core. I think that up to a certain pressure, you can have like some experiments or something like this that can tell you how is the equation of state, etc. But when you go close to the center of the magnetar, the uncertainties about the equation of state and how these may affect solutions.
The physics that I talked about, fortunately, disentangled from the effect of what is happening in the very center where the equation of state is not really known at very high densities. It affects the size of the star. But the physics of the crust in particular, or the outer core, is not affected by that. All these processes that I described would happen in the same way for a magnetar which is 13 kilometers in size or 10 kilometers in size. It's just a little different g gravitational acceleration on the surface, but otherwise it's the same. Like we live on the surface of the Earth, all we care about is the local g. We don't care about what's happening in the center of the Earth, right? A little bit about the curvature maybe, how long it takes to go around, but that's it. Okay, so let's have a break now.